Welcome back, everyone. Hope you enjoyed the little break. We are going to pick up where we left off last time. We saw our acceleration was minus mu direction vector divided by the magnitude of the direction vector cubed plus a miscellaneous force term. Now, for this to become something that we are truly interested in, we are going to want something called pure Keplerian motion. Let's try that again. Motion. There we go. And that just means we are not looking at any of those miscellaneous terms. This will get us constants of motion. Which we will discuss here in a little bit. But first, why is it important to set that force term to 0? It is because of something called conservative forces. And so the textbook definition of conservative forces is just you take an object, and regardless of whatever dynamic path it takes, it always has the same force applied to it throughout that path. It will have the same energy applied to it. But as an example, and I like my examples, you'll see a lot of them in this series, we have a valley. Go ahead and set the baseline. We put a ball somewhere up high towards the top of the valley at a height of, say, h1, and then we drop the ball. Ball will roll. Let me try that again. The ball will roll down to the bottom of the valley, come back up, and come to a stop. And at that moment, the height of h2, you can see, like, without anything else interfering with it, just gravity, you will see that its secondary height is the same as its starting height. But that's not the only unique property about that. If we were to draw an imaginary line, I don't need to draw it that far, but if we would draw an imaginary line through the middle of our symmetric valley here, and we wanted to look at the ball, say, here or here, we would not be able to distinguish between the two of them, really, because not only are the heights the same, but the velocity over here on, let's call this side 1 and this side 2, but the velocity over here on side 2 is going to be the same as the velocity on side 1. And of course, the acceleration is going to be the same throughout. And this is really useful for us for a number of different reasons. But perhaps it's better to start with systems that are famously conservative, are things like gravity. Very fortunately, that's what we're working with. But there are other things like spring forces, which are also conservative. However, like I said at the beginning of the series, we're only looking at gravity, so even though spring force is conservative, we are not going to be taking that into consideration. But what about non-conservative forces? Well, if we redraw our valley that is exactly the same as before, no matter how well the artist does to mess it up, we go to our perfect little valley. We take the same ball to the same height as before, each one, and we drop the ball. We will see when it gets all the way around over to here that at height 2, height 1 is actually going to be higher than height 2. But not only that, when it goes back to the other side, it'll be even lower than at height 2. Height 3 will be even lower than height 2. And this can go on and on and on until you get to a point which I'll say that this is point infinity. So at a height at point infinity, we will see that the velocity of point infinity is 0. There is no more useful motion to be had. There's no more useful energy to be had in that system. It is stagnant. And quite famously, the biggest non-conservative force that you will come across is going to be friction. Friction of some kind. So, with that in mind, let's take a look at something called specific angular momentum. Which has a vector notation and a scalar notation. You can have a vector specific angular momentum and a scalar specific angular momentum. But before we talk about angular momentum, let's talk about linear momentum. Which is denoted as P. And that is just mass times the velocity. And if you wanted to have that be specific momentum, lowercase p, you divide out the mass, so you just have velocity. All right, you know it's going to be serious when I give it its own page. So I did not describe what I meant by specific angular momentum. What I really wanted to point out was that this was mass specific. So it is the angular momentum per kilogram, per pound mass, per slug, per stone, per... I don't know of any other mass units. But there are probably more. Anyway, not the point. So why do we care about mass-specific angular momentum? Why do we care about mass-specific anything? Well, I'm glad you asked. We have the Earth, and we put in orbit around it the Moon. And we put in orbit around it also... Let's see if I cannot draw the smiley face. That's okay. It's gonna do that. We put the satellite and the moon in the exact same orbit, 180 degrees apart from one another. We are going to see that the angular momentum of the moon is going to be way, way, way higher than the angular momentum of the satellite. We don't really care about the mass, though. We only really care about the geometric properties. These have the same orbit. These have the same orbital characteristics. So if we take the mass out, you'll see that the properties will all line up. So there are a few other units that are mass specific in this series, but this is the motivation behind them. It's because if we take the mass out, we can just get the geometric properties of the orbit. That's really all that there is to it. All right, and I shall return you to it. Specific linear momentum is just velocity, which is why you don't see specific linear momentum anywhere. So angular momentum takes a look at the momentum around an orbiting body. So if we have an orbiting body around a host body at a distance of r1 and a velocity of v1, well, this has a momentum all its own. And in fact, let me go ahead and write in that it has a momentum, p1. Then if it's over on this side, if it is a non-circular orbit, it's going to change its distance from the host body and not only is our momentum pointing in a different direction, but it is also a different magnitude. Not to worry, because while magnitude of P1 is less than the magnitude of P2, the magnitude of R1 is greater than the magnitude of R2. It is further out. So there is something to be had here. In fact, you'll see that angular momentum is just the distance to the body crossed with the momentum of the body. And so with what was above, you can see that specific angular momentum is really just r cross, and since we are using specific angular momentum, we want the linear momentum that does not have the mass term, i.e. it est that term. So r crossed, I'm going to use dot notation, r dot. And there you have it, the equation of our specific angular momentum. But it's not quite enough to say that this is it and walk away. Let's prove it. So specific angular momentum is a constant of motion. That means that throughout time, a change in time, it should not change. So let's test this. Always a good idea to test things. So the time derivative of h, we can say that's h dot. That makes it easier to write in the future. And the derivative of the first times the second. And even though these are cross products here, it is still a multiplication, so we can, for the purposes of derivation, treat it like a multiplication. Plus the first times the derivative of the second. And for those of you who are not immediately aware, whenever you see a term crossed with itself, you know that it's always going to go to 0. So let's go ahead and write that down. 0 plus r crossed with, we already know what our acceleration term is minus mu distance, magnitude of the distance cubed. And we can look at it and say, great, we've traded out one complex term for 3 slightly less complex terms. Not so fast, because that's all a scalar. Yeah, I'm doing a voiceover over all of this because I spend the next 25 seconds trying to tell you what I'm doing here, and it's all bad. So instead, I'm just going to tell you that there is an edit that's going to be coming down the line here in like 15-20 seconds, and that should hopefully do a better job of explaining what the motivation is here than what I did originally. One of these days, I'm going to be able to multitask. Today is not that day. So then we have our first term, and it is crossed our second vector term. And as we saw above, that goes to 0. All right, I want to take a minute or two to just discuss what I meant when I was describing what was happening here. Because, boy, did I throw a word salad at you. All right, so to begin with, that whole thing is being multiplied together. And because it's being multiplied together, we can put any of the terms in any order that really suits us. So I just dragged it out to the front here. But let's also do a proof of that. So we have vector r, r1, 2, 3. Here are our vector components. And we decided that we wanted to have a cross product with some multiple of itself. So let's set this up. I'm going to use Cartesian here for the first row. It doesn't really matter, but I'm going to use Cartesian because it's my series. I get to choose. So we have 1, n times r1. Give me just a second while I write all of this stuff in. Right. So then we multiply it out. So for our I term, cross product those two. And 3. And there you go. There's the first one. We'll do the same thing with the other two. And because these can be multiplied in any particular order, and R2, R3, and R2, R3, well, these can be canceled out. They negate each other, as does this, as does this. Therefore, we'll always get a 0 vector. There you go. Now you know what I was talking about when I was trying to describe what was going on there. All right. Let's get back to it. Goes to 0. Therefore, the rate of change of the angular momentum is 0 minus 0. Well, there you have it. It does not change with time. Very useful. Let's do one last thing before signing off. Let's run through a really, hopefully quick example. So we have a body orbiting the Earth that is at a distance of 16,365.424. 0, and I will explain here in a moment what each of these terms means, what each position in this vector means. In terms of kilometers, we have a velocity for that body. You know, it is probably worth noting that this is a distance from the center of the host body, which for this example is Earth. I really put down a closed parentheses thinking it was an H. Great job, me. Our velocity, carrying on like nothing happened. It's in kilometers per second. Fantastic. Now, R, that is just 16,065.4, 0.4556. This is everything in the radial direction. So moving into or moving out of the Earth. We have theta hat. This is everything that is tangential to the Earth. And it is worth noting that your radius should never, ever, ever have a tangential component to it. But your velocity, oh, it has a tangential component. And then I'm going to use Z here, just because orbital motion is in a plane. So this term right here is not super impactful, because if you set everything up right, you should have zeros in this column. But it is useful for afterwards, because so the UR direction, we have 0 times 0 and 0 times 5.34, which is 0 minus 0. R, that's an R. Now that's an R. There we go. The U theta direction, we have 0 times 16,000, 0.4 times 0. So we have another 0 minus 0. The U theta direction plus, and here's where it gets interesting. We have 16,000 here. We have 0 times 0.4 here. All right, so which is going to be 87,481.37399 minus 0, the UZ direction. And I like using as many decimals as possible on my calculator during intermediate steps. It helps me to get a more accurate end product. You can do whatever you want, but this is my suggestion to you, that you do the same. Now, we move on. Well, we have 0, 0, and 87,401.3. I'm not going to include the decimal there. That is in kilometers per second. And no, it is not. It is in kilometers squared per second. There we go. And that can look like a weird unit on the outside, but there are two different ways to process it. The first is that we have a distance times a velocity here. So our distance is going to be in kilometers. velocity is going to be in kilometers per second. Therefore, kilometers squared per second. Another way of looking at this, the pen will work. There we go. Is that if we have some ellipse in a given second, we are tracing out an area of our arc that is going to cover 87,400, let's make that look more like a 481 square kilometers every second, no matter if it's over here where I previously drew it, or if it's over here. It will always be the same area of the ellipse traced out every second. And I think that's a good enough stopping point. Thank you so much for stopping by. I look forward to talking with you again in the next episode.